So now we're going to talk about distance and displacement. And you may remember from last time I pointed out in the table that distance is a scalar and displacement is a vector. And we're going to talk about that in a little bit more detail now. So you are going to be on page 8 in your yellow packet taking notes. So at the top here, motion along a straight line is what we're concerned about when we're talking about one-dimensional motion. We're going to do a little bit of two-dimensional motion, but for the most part, we're only going to be talking about things moving along a straight line, so left and right or up and down. And this actually occurs somewhat frequently, motion of a train along a straight line, an object like a ball falling vertically down to the earth, the oscillations of a spring bouncing up and down are some good examples of one-dimensional motion. So there are 3 different ways to describe a location. You can describe something's position, you can describe something's distance from a reference point, and you can describe its displacement. So the first one of these we're going to look at is position. So position is the directed distance of an object from a reference point. So here you can see the little sketch. There's a potted plant here, which is our reference point. And the person over here on the left, this is his initial location. He's 11 meters west of the reference point, and that is what his position is. And then at some other time, he's at D2, which is 22 meters east of the reference point. So that's position. And just saying that something is here or there is not very helpful when we're trying to talk about motion and describe motion, which is why we are paying attention to these locations, distances, and directions. So now distance and displacement are fairly similar to each other. Distance is a scalar, and it's how far an object has traveled while it's moving. And displacement is a vector that shows how far an object is from where it started. So we're concerned with our final position minus our starting position. So we've got a good sketch here. So initially somebody is at A and they want to go to B. Now they could take this wandering path to get to there because maybe there's a building in the way or a tree in the way, and so they can't take a straight line path. And so the distance they traveled is however long this path is. Whereas displacement is actually the measurement of how far it is from point A to point B. And so what we care about is that if we're looking at this, that B is to the right of A. So it's going to be so much distance, so many inches to the right of A. So in this case, since displacement is a vector, it always needs a direction, and distance is a scalar, and it does not need a direction. So checking your understanding, if you run around an oval track with a perimeter of 350 meters and end where you began, what is your distance? So if you've got this oval track and you start here and you run around, the distance that you traveled is 350 meters. But your displacement, you're comparing where you start and where you end. So if you start here and end here, your displacement is 0. And there's no direction because it is 0. So distance and displacement can be very different. So distance has no direction, it's a scalar. And displacement has a direction, but in this case, since it is 0, there is no direction. So is it possible for the total distance traveled to equal the magnitude of the displacement? If no, why not? And if yes, give an example. So yes, this is possible. So if the path that you took is exactly a straight line from the starting point to the final point, your distance is going to be the same as your displacement. If you're just looking at the magnitude in the units, but you're not concerned with the direction. Number 2, is it possible for the total distance traveled to exceed the magnitude of the displacement? If no, why not? If yes, give an example. So yeah, the example that we already saw was We've seen 2 of them, so you could take this meandering path. So your distance could be this path, whereas your displacement would just be the straight line. We've got the loop where you start and end at the same location, so your displacement is much shorter than your distance traveled. Then number 3, we're looking at just the opposite. Is it possible for the magnitude of the displacement to exceed the total distance traveled? If no, why not? And if yes, give an example. Well, no, because you can't be farther away from your starting point than the actual distance you traveled. So there is no way that this displacement can be shorter than your distance. So you've got to think about that for a moment, because you got to recall the definitions. The distance measures the path traveled, and the displacement is how far you are away from the starting location. So we've got a doodle note sheet, and this is on page 9. 3 distinct ways to describe location. So we've got distance is the total length of the path traveled regardless of direction. It's a scalar quantity. And this is what your car's odometer reads, like 80 kilometers. And we typically write it as a D, and it has no lines or bars or anything above it. Position is the location of an object relative to a reference point. It is a vector quantity. The car's position is 25 meters west of the library. So we gave ourselves a reference point. We gave ourselves a direction. We normally write this with a D with what we call a vector hat over it. It's got this half of an arrowhead. We're not going to use that a whole lot, but you're going to see it in a lot of the reference material to designate that that is a vector as opposed to a scalar. And displacement is the change in position, and it's also a vector quantity. So an example is the rabbit hopped from 5 meters east of the carrot to 15 meters east of the carrot. The rabbit's displacement is 10 meters east. So this is the delta, or the change in position, and so that's going to have a vector hat on the top. So this triangle means delta, and it just means there's a change. So we're going to take the final position of D2 minus D1 to figure out how far away you've moved. So pause the video, copy this information down. So the bottom half of this has a couple of examples. So Xavier travels to Yvonne, and how far does he travel, and what does this value represent? So he travels 110 meters plus 70 meters, so that's 180 meters, and that represents the distance because there's no direction, and that's the path that he had to take going on the street. But if he was a bird, he would be able to fly straight over there, which would be like a Pythagorean theorem hypotenuse problem. We're not going to worry about doing that because, but it's important to recognize that this is a displacement problem. Okay, I'm not concerned about the actual value and the angle and all of that. We're not going to do a whole lot of that. But I want you to recognize that in this case, the displacement is very different than the distance. So the Think About It says a raceway is designed as a loop in which one lap is 4 kilometers. If a race car completes 200 laps, what is its distance traveled? So it's going to be 4 kilometers times 200 laps, and that's going to give us 800 kilometers. And then the position at the end of the race relative to the starting point, well, he's right back where he started, so he's 0. And his displacement is also 0 because he's back in the same place. So again, pause the video, copy what you need to, and you really don't need to worry about the angles and this whole Pythagorean theorem calculation. So what I'm going to have you do right now is work on yellow pages 6 and 7, and then I'm going to go over those in the next video. So we already did questions 1, 2, and 3 on page 6. So you should be starting with question number 4 and continuing on to the next page, and I will pick up there and go over the answers in the next video.